Thank you very much, Dr. Viotti, for the excellent presentation in this difficult theme. Thank you very much. And now for our last lecture, I'll call Professor Mina Popovic. Dr. Popovic is a scientific director of the Eugin Group in Barcelona and the coordinator of Escher's special interest groups in stem cells. And her lecture will be the impact of diagnosing mosaicism in PGT-A. Thank you very much.
Thank you. Thank you very much for the introduction, and I would like to thank the Huntington team for this invitation. It's really a pleasure to be here, and especially a pleasure to have the opportunity to talk about some of the work that we have done on looking at the impact of diagnosing mosaicism on PGT-A. And I often refer to mosaicism as the ultimate diagnostic dilemma because there's still really no clinical consensus on whether we should diagnose it, how we should diagnose it, and what we should do with mosaic embryos. And even in this session, we might sometimes challenge each other's opinions as well. So I don't have to tell you much on this, but basically we all know that embryo aneuploidy is a major factor influencing human reproductive success. We know that the frequency of aneuploid embryos increases with advancing maternal age, leading to a decrease in fertility. However, it has been suggested that ongoing pregnancy rates remain stable across all maternal age groups if a euploid embryo is transferred. So the selection of euploid embryos should theoretically improve clinical outcomes, and this is really the premise for PGT-A. Given its inherent appeal, the use of PGT-A is increasing, and these are just some statistics from the US from 2018, where around 40% of all ART cycles included PGT-A, and I think these numbers are increasing, and also that the use of PGT-A is quite prevalent here in Brazil as well. As we've already heard, we know that PGT-A relies on a trophectoderm biopsy combined with next-generation sequencing at the moment. However, what complicates PGT-A is that the origin of chromosomal abnormalities in human embryos is varied. So if an error occurs during meiosis, it will be present in the beginning, so largely during oogenesis, and this will actually lead to all the cells within the embryo carrying this abnormality. And this is what we refer to as uniformly abnormal. So in practice, we see profiles like this. So at the bottom, we have the chromosome number. These reads, we want them to be around 0, which would indicate diploidy. However, if there is a deviation, like we see here, and it's reaching the threshold of what we would consider a uniform abnormality, so in this case, a trisomy 16, we can be confident that this embryo is abnormal, and of course, we would not transfer it. Here as well, we see another example of a monosomy 16. So again, this abnormality is reaching the threshold of what we would consider a uniform aberration. However, abnormalities can also originate during mitosis that underlies embryogenesis. And here, only some of the cells within the embryo will be abnormal. So what we refer to as chromosomal mosaicism, as Manuel already described. And in this case, we see profiles where we see an indication of an abnormality, but it is not quite reaching the threshold of what we would consider a uniform abnormality. In this case, the values are around minus 0.5, which would suggest that around 50% of the cells within this biopsy carry this abnormality. And we can now actually classify mosaicism as low level or high level, depending on the percentage of abnormal cells within the biopsy. So less than 50% is low and more than 50% as high. And as Manuel already discussed, we see that blastocysts that are classified as mosaic have the capacity to result in viable pregnancies, but it has been suggested that they do miscarry more. However, diagnosing mosaicism is really hindered by several biological and technical challenges. There are still lots of reservations regarding the clinical value of diagnosing mosaicism, and this really complicates embryo transfer policies. And we are still unaware of all the risks that transferring mosaic embryos may carry, so this still raises some concerns. And also, there are a lot of differences in diagnosing and reporting mosaicism. So there are different thresholds that are actually used to call an embryo mosaic. So in some cases, embryos that are diagnosed with 20 to 80% abnormal cells are referred to as mosaic. In other providers use a threshold of 30 to 70%. And in some cases, actually all mosaic embryos are classified as clinically unsuitable. So any embryos that are diagnosed with more than 30% abnormal cells are just classified as abnormal. And in some cases, mosaicism is not reported at all. So embryos diagnosed with less than 50% abnormal cells are actually classified as euploid or clinically unsuitable. In the first case, where we actually diagnose mosaicism, in mosaic embryos are actually classified as a third category of embryos with assumed reduced potential. However, all of these differences in diagnosing mosaicism and reporting mosaicism may actually impact the number of euploid embryos that are available for transfer. And these are just some data from the START trial where we can see an indication that when mosaicism is not reported, this leads to higher euploidy rates across some centers. One thing we have to keep in mind is that the great challenge of PGT-A is that we are starting with low amounts of DNA. And what needs to happen with this DNA is that it undergoes a step of whole genome amplification. Of course, we hope for an even amplification. However, the amplification can be biased, and this can lead to an over or an underrepresentation of certain parts of the genome. So we cannot assume that this intermediate copy number value unequivocally predicts mosaicism and blastocysts, because sometimes this technical noise due to artifacts of amplification may actually be indistinguishable from mosaic results, and this further complicates diagnosis. So we have looked at mosaicism in different aspects. So we first wanted to look at the overall accuracy of pre-implantation genetic testing for aneuploidies when mosaicism is diagnosed. And we also wanted to consider the impact of diagnosing mosaicism on the availability of embryos for transfer across different providers and clinics. So for our first approach, we used a more, say, fundamental basic science system. So we use this extended in vitro culture model of human embryos. This system allows us to plate embryos on day 6, and actually they form outgrowths, as you can see here. And when we stain these outgrowths, we see that they show phenotypes that are associated with post-implantation development. So we can culture the embryos up to day 12. So we have now performed this culture on 230 blastocysts. So these are PGT embryos with different diagnoses. So first category were uniformly aneuploid embryos. So we have 158 of these embryos. Of course, most of them because they are the easiest ones to get for research. Then we also had a number of mosaic embryos. And here we have 2 different types. One are embryos that have an aneuploidy in addition to the mosaicism, so they're uniform aneuploidy and a mosaicism, and some embryos that are mosaic only, so only one mosaic abnormality. And then also we had a number of embryos which were our euploid controls. So we cultured these embryos to day 12, and then after that we selected 66 whole outgrowths which we then collected for sequencing. We also were able, for 24 embryos, to collect portions. So we separated them into parts to also look at the chances of mosaicism within these outgrowths. And for these, we collected 90 samples. So in total, we had 156 samples from 19 embryos, and this includes both the whole outgrowths and also the portioned embryos. So the first thing we looked at were the developmental outcomes of these different embryos. And what we actually observed that is around half of the embryos actually remained attached throughout this extended culture, and they remained viable at day 12. where the other half actually detached. So around day 8, we see that these embryos are completely degenerated. So then we correlated these developmental outcomes to the original trophectoderm biopsy results. And what we actually saw that embryos with trisomies and duplication, so chromosomal gains, had similar results to the euploid embryos. So they were more likely to remain attached compared to embryos that contained monosomies, deletions, or multiple aberrations. We also looked at the effect of these abnormalities on development. And what we can see is that embryos with monosomies and trisomies actually had lower numbers of epiblast-like cells, so OCT4 positive cells, and also lower numbers of primitive endoderm cells. So they looked quite different in the stainings, as you can see, to the euploid embryos. So it seems that these abnormalities are definitely impairing development. We then looked at the correlation between the uniform abnormalities and the results on day 12. And what we can see is that these results were always concordant. So these abnormalities that are uniform, they really persist throughout development. We also established 100% concordance when reporting euploidy. So if we look at here just an example of a whole outgrowth, this was a blastocyst biopsy that was euploid, and we can see also that the outgrowth is euploid. Here is just another example of an embryo that we actually separated into parts, and again we see a original euploid diagnosis, and we can see that this is confirmed in all portions of this outgrowth. What about the mosaic embryos, though? Well, for the mosaic embryos, 80% of them actually remained viable throughout the extended culture. And when we look at the phenotypes of these embryos with staining, we can actually see that they had similar phenotypes. And on day 12, 69% of these mosaic embryos were actually uniformly euploid. So here are just some examples of different embryos. And the first one we have mosaic, originally diagnosed with a mosaic monosomy 9. And as you can see, there's no evidence of this abnormality, mosaic monosomy 8. And these two are actually low-level mosaics. And here we have high-level mosaics, so a mosaic monosomy 18 and a mosaic deletion on chromosome 20. And we see that these outgrowths are euploid. So this is just an example of an embryo that we separated into portions. So here we had a blastocyst biopsy with a mosaic monosomy 16, low level. And when we look at the different portions of the outgrowth, again, we see no evidence of this aberration. However, on day 12, 27.6% of mosaics were actually uniformly aneuploid. And what is important to note here is that all of these were diagnosed with high-level mosaicism. So here we have an embryo with a mosaic trisomy 21, and as you can see in the outgrowth in all the portions, this embryo actually had a uniform trisomy 21. We did reveal evidence of true mosaic configuration. So mosaicism definitely does exist. And this was an embryo that was diagnosed with a mosaic monosomy 7. And we can actually see a reciprocal event in the outgrowth. So this is really evidence of a mitotic era leading to mosaicism. So here we have trisomy 7 in one of the portions, another portion was euploid, and the third portion had a mosaic monosomy 7. So what we can conclude for this first part is that we see 100% concordance for whole chromosome uniform aneuploidies. So this is reassuring for PGT-A. Meiotic abnormalities persist within the embryo. Positive predictive value, though, is considerably reduced when diagnosing mosaicism. And false positives are largely attributed to diagnosis of mosaicism. So this does raise significant concerns really regarding the accuracy, but also the relevance of these mosaic predictions. So we also then wanted to look at the effects of diagnosing mosaicism on the availability of embryos for transfer across different providers and clinics. So for this, we did a retrospective analysis in which we reviewed over 36,000 consecutive PGT-A results. So this was an international multi-center study performed across our group and also with external collaborators. So we obtained results from around 10,000 patients in close to 12,000 cycles. And the cycles were performed between October 2015 and 2021. And a total of 17 IVF centers across 8 providers and 5 countries participated in the study. So as I mentioned, we had 8 different providers. Some of these providers served only one clinic, whereas you can see some providers actually served several different clinics. And we used a multi-level mixed linear regression to compare associations between the PGT-A providers and the outcomes. We controlled for several confounding factors. And our results included, our database included both autologous and oocyte donation next-generation sequencing-based PGT-A cycles and excluded PGT-SR cycles. We also evaluated mosaic embryo transfer rates across 15 clinics, and this includes outcomes. So we looked at the outcomes of these transfers. So just looking at some of the patient demographics. So as I mentioned, around 10,000 patients in our study. The mean maternal age was 36.2 years and paternal age 40 years. And also, we had some around 10% of oocyte donation cycles. But as you can see, there is quite some variability amongst the providers. So some had 0% up to 29%. And what we observed is that different providers we see different approaches in diagnosing mosaicism. So provider A, for instance, did not report mosaicism. They only reported embryos as either normal or abnormal, whereas providers B to H reported embryos also as mosaic. But as you can already see, there seem to be some differences in these mosaicism rates. Overall, the total number of euploid embryos, the frequency was 44.9%, and 49.4% of embryos were abnormal, and 5.7% mosaic. So then we looked at different predictors of euploidy and mosaicism. So we observed, of course, that maternal age, with advancing maternal age, there was a lower odds of diagnosing euploidy. And also we observed that embryos that were biopsied on day 6 and day 7 compared to embryos biopsied on day 5 had lower odds of diagnosing euploidy. We also observed that paternal age and the number of embryos biopsied had no effect on euploidy. And when we look at the different clinics reporting to a provider, so we also wanted to look at the effects of the clinics in this case. What we observed for the clinics that use provider F is actually no effect on diagnosing euploidy, and also no effect on diagnosing mosaicism. However, when we look at the clinics that use provider H, we do see some differences in euploidy. So clinic A1, for instance, has higher odds of diagnosing euploidy. However, we didn't see any differences in the chance of mosaic diagnosis. In the end, the provider, in fact, had the strongest effect on PGT-A results. And what we observed in terms of mosaicism is really vast differences in the rates of mosaicism. So as you can see, ranging from 3% from some providers up to 25%. And we observed that several providers had higher odds of diagnosing euploidy, whereas the odds of diagnosing mosaicism were lower for provider B, provider C, and higher for provider E. We also looked at the chance of having at least one euploid embryo available for transfer. And we saw that the odds were higher in those providers with significantly lower rates of mosaicism and the provider that actually did not report mosaicism. We also then compared the overall chance of having at least one euploid blastocyst available for transfer between the provider that did not report mosaicism and all the other providers that did. And we can see that the chance was higher when mosaicism was not reported. So in provider A compared to all the other ones. We also looked at this by using adjusted rates. And again, we see that the providers with the highest euploidy rates actually had the lowest rates of mosaicism. And also, when we look at the chance of having at least one euploid embryo available for transfer, the chances are higher for those providers with the lowest rates of mosaicism. We also looked at rates of single mosaic abnormalities across the different providers. So as you can see here, we do see quite some differences amongst the providers, whereas when we look at single uniform aneuploidies, we see that these calls are quite consistent. We also looked at these diagnoses across different chromosomes. For single uniform aneuploidies, we confirmed previous reports where abnormalities that affect chromosomes 15, 16, 21, and 22 were the most frequent. However, for the single mosaic aberrations, we don't see much of a pattern. However, we did see a significantly higher number of mosaic trisomy 19. And this was a very interesting result for us because we know that actually sequencing chromosome 19 is very difficult. So what this suggests is more a technical variability rather than true biological mosaicism. So finally, we look at the clinical outcomes following the transfer of mosaic embryos. So as I said, this included a total of 245 mosaic transfers. But what is important to note, in fact, is that if we look at the rate of mosaic embryo transfers, we can see that this really varied amongst the providers, where some providers did not transfer mosaic embryos at all, and in other providers, around 36.5% of mosaic embryos were transferred. But overall, what we see is that only around 13% of all mosaic embryos actually end up being transferred. And when we look at the live birth rate, this was around 35.2%, and the miscarriage rate was around 5%. So these embryos do have potential. We confirmed that. And when we look at the results compared to euploid embryo transfers, we can see that the live birth rate was basically the same, around 35%, and miscarriage rate of around 5%. And we actually, when we did a non-inferiority comparison, we actually see that there were no difference between outcomes in euploid and mosaic embryos. We did this comparison amongst all clinics, but also for Clinic F, because these had the most mosaic transfers. And one thing that is important to note here, that our database of mosaic embryo transfers included largely low-level mosaics. So we only had 3 transfers with high-grade mosaicism. So these results apply for low-level mosaics. So overall, what our results revealed is a strong association between the genetic testing provider and PGT-A results. We showed that classifying mosaic embryos as mosaic may actually come at the expense of euploid diagnosis. And despite their normal developmental potential, close to 90% of mosaic embryos are just not used. There is still a very high risk perception surrounding mosaic embryos. And differences in mosaic diagnosis across PGT-A providers seem to point to a technical bias as opposed to true biological variability. I'm not denying that mosaicism exists. It surely exists, but perhaps not to the extent that we are reporting it. So our findings really highlight a strong need for standardization and quality assurance in the industry. And false positive diagnosis may actually play a role in the failure to demonstrate improved outcomes with PGT-A. There is so much variability in the literature surrounding PGT-A. So with current practices, as I said, we really might be limiting the clinical utility as we are excluding potentially viable embryos. So until we can be sure that the diagnosis of mosaicism really accurately reflects biological variability, reporting mosaicism, and especially low-level mosaicism, really remains difficult to justify, as it may really determine a difference for a patient between success or failure. So with that, I would like to thank all my collaborators, all our collaborators on this project that included several clinics within the Eugin group and also external collaborators. And thank you very much for your attention.